This is Lab 4, Rope Physics Spring Mass Objective. Analyze the objective of spring mass that oscillates a motion similar to that of the extreme sport bungee jumping. The analysis is done by combining fundamental principles, momentum and energy, and applying other fundamental laws already studied, Hooke's law and Newton's second law. Based on lab materials, spring mass video, I start analyze the oscillation motion by loading it into track viewer. Here I choose the two dimensions coordinate system, x horizontally and y vertically, with positive direction down. Also, I calibrated the system using a calibration stick and considering 0.7 meters from origin of the already established coordinate system to the starting point of motion. This starting point is considered being the living object free after tensioning the spring. I consider the reference point of the object, the contact point between spring and spring mass, and I started figure the positions taking into consideration the video frames with a frame rate of 10.53 seconds and the frame delta t of 0.095 seconds, so a total of 58 frames. Now the tracking viewer is prepared for analyzing the oscillation motion of the spring mass. I choose the initial position considering the moment t equal to 0 and the final position at t equal with 5.508 seconds. Having all the data extracted from the tracker, I establish the initial conditions of movement in order to insert them into Python program for building the computer model. First of all, the initial time and position are based on the extracted data. I obtained the motion graphic representation. From this graphic, I extracted the first three periods needed to calculate the period average, so the oscillation period is t equal with 1.61436 seconds. Now I can determine the elasticity constant K equal to 6.0897 Newton over meter. Writing down the equation of static equilibrium, I extracted the elongation L0 and doing all the necessary calculation, I obtained L0 equal to 0.0532 meters. The initial conditions as spring mass and object position and the obtained results as elasticity constant and elongation are inserted into Python program as interaction initialization. Applying Newton's second law, gravitational force plus spring force equal to net force, and having the magnitude of gravitational and spring forces, I determine the velocity variation based on the momentum, net force equal to delta momentum over delta t. After that, I apply the law of energy conservation, taking into consideration all types of energy, kinetic energy, gravitation potential energy, and spring potential energy. In Python program, I set up the initial energies and their time variation, and finally the computer model runs, showing on the same display the motions of the experimental model, red ball, and of the computer model, blue ball. Also here are shown the gravitation force vector, black arrow, and spring force vector, blue arrow. Finally, the Python program shows all energies: kinetic energy, blue curve, spring potential energy, red curve, gravitation potential energy, green curve, and total energy, the sum of the three above mentioned energy, with yellow curve. The comparison between the red ball as experiment motion and the blue ball as computer model motion gave me good results. The motion of the blue ball is continuous, and the motion of the red ball seems to have a non-continuous motion, like a jump, due to the frame rate and the frame delta t. This delta t in the experiment model is 0.095 seconds, much longer, about 29 times, than the delta t used in the computer model, which is 0.005 seconds. Python program displays these two motions on the same graphic, where we can observe the differences. More explanations can be done by the relative point mass establishment for each frame of experimental motion. Also, the approximate calculation of the oscillation period gives difference at the end of motion. The experiment model has an advance from the computer model. Concluding, the obtained results are quite good, as shown in the graphic: blue curve for computer model and red curve for experimental model.